don't feel bad if all of this hypothesis testing stuff is kind of throwing you for a loop at first, because it will for a while. It takes a lot of practice, and it takes sort of a shift in your thinking. Like I said when I was defining p-value, our brains want to think of it the other way. Given the data that I just saw, what's the probability? What's the chance that the null could be true? Well, that's not technically what a p-value is. It's the other way around. Given that the null is true, what's the chance I could get data like this? That's a p-value, right? But the decision you make as far as reject the null or fail to reject the null doesn't matter which of those two ways you think of it. You'll still make the right decision. Just know that P is for probability, and if it's small, then the probability is not good that the null hypothesis is true. So you reject it. Small values of P. Okay, small enough, alpha. Okay. So alpha is our cutoff for how small a p-value has to be. Okay? Other questions? No? All right. We're going to do section 10.4, which is the same stuff, but for proportions. All right? So when we do hypothesis tests for population proportions, this will mimic what we did when we did confidence intervals for population proportions. Same assumptions have to be met. The same procedure on your calculator will be used, except it'll have a test at the end instead of an int at the end. Right? So on that tree diagram of deciding what type of procedure to use, means or proportions, this is proportions. One sample or two, this is one. All right? So that's where we're at now. Chapter 11, we get into two sample problems for hypothesis testing. Okay, so steps are always the same for hypothesis tests. State the null and alternative hypotheses, determine which distribution, and for me, instead of distribution, which procedure on TI 83 or 4, right? Because that does tell you the distribution. Is it a Z interval or a Z test, or is it, that's what I want you to do. So step 2, figure out what am I doing on my calculator, right? That calculator will give you the test statistic and the p-value. All right? State the level of significance. That's what we were talking about over here with alpha. Gather data. Calculate the necessary statistics using that procedure. All right? Using that. And then draw a conclusion and interpret the decision. This, step number 4, has two parts to it. Right? The first part is this statement. I'm going to reject the null, or I'm going to fail to reject the null. But that's not the conclusion. That's not, I'm sorry, that is the conclusion. It's not the interpretation. So what's the interpretation?
There is sufficient data, or there's not sufficient.
Right, exactly. There is sufficient evidence to support the claim, or there is not sufficient evidence to support the claim. Only don't say the claim. Say whatever it was in the context of the problem. So we're just going to practice that a bunch today. All right? So, assumptions. Remember the assumptions for proportions problem. Samples have to be, first of all, what? Random. So we got to have random samples. So as long as we have random samples, then conditions for binomial distribution are met. Basically, that says this is a proportions problem, right? Proportions problem, but binomial means that you have two possible outcomes. You got a fixed number of trials. Oh, that's my sample size. And each of those trials are independent, and that's the big one, right? They need to be independent. But then in order to use the normal approximation to the binomial, then our central limit theorem rule has to be met. And that's, tell me again, what NP greater than or equal to 5 and N times 1 minus P greater than or equal to 5. Say that in English. Good. 5 successes, 5 failures. Right? 5 successes and 5 failures. If those are all met, then we can approximate with a normal distribution, which means we can use which function on our calculator? Go to your calculator, push the stat button, go over to tests, and see if you can tell what we're going to use for a one sample proportions hypothesis test. You got it? What do you think? Right. One prop Z test. One prop Z test. Right? So if all of these things are met, then we can use this. So that step of determine the correct distribution, that's telling me Z for normal, right? That's what they're talking about. But you have to assure yourself that you can use the one prop Z test by seeing that the assumptions are met. Right? So that's all they're getting at there. Okay, well, the book will lead you through computing a test statistic, but we know by now that our calculator will compute this for us, but you should be aware of this formula. The main thing I want you to understand about a test statistic is what does the value of it tell you? What is a test statistic? Same thing for a T or a Z, the same interpretation. The test statistic, Z in this case, tells us ... Fill in the ... Why are we computing that thing? What good is it to us? Okay, well, maybe we need to review this a little bit. If, what did you say? Okay, it's a standardized score. And standard Z-scores, right, or T-scores are number of what? Good, that's what I'm wanting you to hear. Right? So it tells us the number of standard errors that the sample statistic, in this case P hat, is from the hypothesized population parameter. Right? That P hat is from P0. So what do you suppose P0 is? That notation, without the 0, P is what we use for population proportion, right? I heard somebody say probability. That's also the probability of success on a single trial. So when you sample one individual, the probability they say yes or whatever it is you're doing is equal to the population proportion. Put the sub-zero on it, and what is that? What? Okay, good. No. Yeah. At first I thought you said norm. I thought, I'm not sure what that means, but no. Got it. Right, so P0 is the null hypothesis. How about this? Hypothesized value of P. In other words, the null hypothesis is P and P0 and either an equal or a less than or equal or a greater than or equal. Right? So for all these problems, our null hypothesis will look just like this with one of those three symbols in there. Right? So this P0 is just a number they're going to give us. Test to see if the true population proportion is less than 0.3 or something. They'll give us a P0. Well, the test statistic tells us how many standard errors our sample data is from what we would have expected if the null were true. And if that number's big, we reject the null. Well, that number of standard errors tells you how far out in the tail you get. Right? So does the p-value. So the test statistic and the p-value are giving you two ways of saying the same thing. How far out in the tail did our sample data fall? So I want you to know how to do this. And just like before, the book doesn't put the sub-zero on here, but it should. Right? So this should be p hat minus p sub 0, p sub 0, p sub 0. You don't technically have to have it there, but it makes it more clear of where you're going to compute this thing. In the homework, they're going to say, determine the value of the test statistic, and they'll give you a blank to enter it in. Well, you can get it from your calculator, right? So you can use this formula if you want, or you can just go to 1 prop z test, do it, and up will pop z equal, and they'll give you the, and it'll match. It'll match to a lot of decimal places. So, okay. So we know all that. Here it says, for each scenario, identify which distribution should be used to test the claim. Well, instead of distribution, I say 1 prop z test, right? So here it is, can we use 1 prop z test? I want to reword that first sentence, but there's going to be 3 of these. So on this first one, at least 15% of listeners of nonprofit radio stations generally favor commercials for other nonprofit organizations on the station. A local nonprofit radio believes that it's less than 15%. The station plans to survey a simple random sample of 50 to test its claim. Are we going to meet the assumptions for 1 prop z test? Assumption number 1, random sample. A simple random sample of 50. So that one's good. Binomial distribution. They either support it or they don't, right? Or in favor or they're not. So 2 outcomes. Fixed number of trials. Yep. Are those trials independent? If it's a simple random sample, then yeah, they'd be independent, right? Because I'm not asking, all the same people in the same house or anything like that. It's just a random sample, right? So all that's met. Now we have to check the sample size. Do we get what is it we have to check? 5 successes, 5 failures. Well, if it's 15%, what's 15% of 50? In other words, P times N equals 50 times 0.15. What is that number? 7.5. So it is bigger than 5. Not a lot bigger than 5, but it's bigger than 5. Now, if you got a sample of 50 and you got 7.5 expected successes, how many failures do you expect? A lot more. Plenty. Right? It's going to definitely be bigger than 5. So I don't even have to compute it. But the rest of the 50. So 42.5. Right? So that one, yes, we can use 1 prop z test. What about this one? 10% of students turn off their cell phones during classes. Man, I hope it's more than that. Aggravated with the number of cell phone rings, the professor believes that fewer than 10% turn off their cell phone. Test is claimed by a simple random sample of 20. No, why not? 10% of 20 is 2. So we only would expect to see 2 successes in that sample. So we're not going to meet the 5. So that one's a no. You cannot use 1 prop z test. Right? I think I put a slide in here, but I'll get to it. But what do you do if you can't use 1 prop z test? I'll talk about that in just a second. Okay, what about this one? The mean amount of rainfall in the southern part of Texas during the month of September is commonly believed to be no more than 3.02 inches. Meteorologist claims that the amount of rainfall has been higher than normal. He tests his claim by measuring amounts of rainfall in a simple random sample of 12 locations. Assume that the population standard deviation is unknown and the population distribution is approximately normal. Yes, what? Can we use one prop z-test? No, why not? It's a means problem. It's not a proportions problem. Prop is for proportion, right? So you can't use one prop z-test. What would you use here? T-test. And is it okay to use a t-test? Does it meet the conditions for that? Yeah. We don't have a sample of at least 30, but the data is normally distributed, so we're fine on that. We've got a simple random sample, blah, blah, blah. Right? So not a proportions problem. Let's see. Here, yeah, I thought I stuck this on there. What do you do in this case where it's not met, for the sample size is not met? What you would use is called the exact binomial method, which is built into software, but it's not built into our calculator. But you could do it easy enough just using the binomial probability. You can compute the p-value yourself. But we won't do that in this class. Okay? So if the conditions are not met, then you just say, well, I can't work this problem. You get off the hook on that one. All right, so this is what we were talking about before. Same old, same old. If you compute the p-value and it's less than your significance level, then you're going to reject the null. Otherwise, you fail to reject the null. Let's see. Let me zip through here for a second. And yeah, this one will work. Here's a problem to work. We'll do the first one together as a class, and then I'll show one and you work it, and then we'll show the answer. Right? And the next one I'm going to show after this comes from your data. Right? And then we'll come back into some of theirs. So here we go. Local school board has been advertising that at least 65% of voters favor a tax increase to pay for a new school. A local politician believes that less than 65% of his constituents favor this tax increase. To test his belief, his staff asked a simple random sample of 50 of his constituents whether they favor the tax increase, and 27 said that they would vote in favor. If the politician wishes to be 95% confident in his conclusion, does this information support his belief? I think there's another paragraph. Nope. I thought it would say, conduct a hypothesis test, blah, blah, blah. Right? But we're going to do it with a hypothesis test. Now, they said it as if they were heading for a confidence interval. 95% confident, but what's the alpha level? 0.05. That goes with 95%. Right? 5% is the error rate, so 0.05. Okay, so first step. Okay, state the null and the alternative hypothesis. So it's the politician's belief that we want to test. And the politician's belief is what? What's less than? I want you to get the symbol right. P. Population proportion, which is P. So P is less than 0.65. Okay? So is that the null or is that the alternative? That's the alternative. So the null is greater than or equal to 0.65. Okay? So we've stated the null and alternative hypothesis. What's the next step? Before you go to the calculator, you got to make sure that it's okay to go to the calculator. In other words, determine what they say is determine the distribution that will be used to test this. What procedure will we use to test it? And is it okay to use that procedure? Well, pretty obvious that this came from section 10.4, but let's go through the questions. What's the first question you should ask yourself? Well, not there yet. Just to, is this a means or a proportions problem? Proportions problem, all right? And you know it's a proportions problem because they talk about a percent. You know, percent, and it's a categorical variable. You're either in favor or you're not. So means problems are always quantitative. They're measuring something, right? So it's a proportions problem. Is it one sample or two? It's one sample. So then we're done asking questions. We then check the requirements to use one prop z-test. So now, random sample, we got that, right? He said simple random sample of 50. All right? Does this apply to the binomial distribution? Yep, it does. How about sample size? We got 27, and 65% would be expected to be successes.
You have 50.
Oh, yeah, I looked at 27. That's the number of successes. 50 is the sample size, so 65% of 50 is well over 5. What did you get? 32.5. They actually got 27 successes. We would have expected 32 if the null were true. We didn't quite get that, but we still got way over 5. And the rest of the 50 are going to be failures, and we easily got 5 of those. So one prop z-test is the procedure that we can use. So now, go to one prop z-test and work it. I'm flashing through some slides here. These are what we've already determined. So our significance level is 0.05, as we said before. But remember, if 95% is the confidence level, we call that C, and alpha is 1 minus C. So 1 minus 0.95 gives us 0.05 for alpha. Alpha is not something you enter into your calculator. It's just what you use to make your conclusion. Okay? So gather data, calculate the necessary sample statistics. In our calculator, when we go to one prop z-test, what does it look like? What's the first thing it asks you? Okay, P from the null. So P0, and it has a colon. What do we enter there? 0.65. And then what's the next thing? X. X is 27, and it's the number of successes. Okay? We'll work a problem in a minute where they don't give us that. We have to figure it out. And then N is 50. And next thing is choose the alternative, right? Okay? So I think on your calculator it's P, then a colon, and then, is that right? P, then a colon? And then a not equal P0, a less than P0, or a greater than P0. And we want, well, to decide, we come back over here, look at our alternative. This is P0, so we want less than P0. So choose that one, calculate. So when you do that, you get, first of all, a test statistic, Z. What is Z? Negative 1.631. Is that big? Remember, that's number of standard errors that the sample data is from the null hypothesis. 1.63 standard errors. Not really. If it gets out around 2, we start to get excited. But around 1.6, maybe not so much. What's the p-value? Now, it's a little tricky when you go to these prop tests, figuring out which is my p-value, because there's several p's in there, right? When it's a one-sample problem, there's 2 of them. One of them is just p, and one is p with a blob over the top. And the one with the blob over the top, that's their attempt at a hat, right? Is it go in this order, P first? Then, okay. So what is P? 0.05147. And that's the P-value. Then the P with the hat is point what? 5.4. Yeah. Okay. And that you should be able to confirm by hand easy enough, and it's a good check on it did I enter the data right? So that would be 27 over 50. All right? Okay? Now our alpha is 0.05. our p-value is 0.05147. So it is greater than alpha. So what's the conclusion? So fail to reject the null. And what's the interpretation of that? Remember, the interpretation should be in the context of the problem. We got a politician, we got a tax increase, we got, what are we saying?
There is not sufficient.
Good. There is not sufficient evidence to support the claim that, and what is the claim in the context of the problem? Very good. Less than 65% are in favor. And I'm kind of abbreviating a little bit, but in favor of the tax increase. Now, I want to make a little point here, and as a statistician who works frequently with researchers, scientists, I have a little soapbox that this 0.05 cutoff is not some magic wall or more like a cliff that you fall off of. It's more like a hill. Remember what a p-value is. Well, let me ask you this question. If the null is really true, and it is at least 65% of the population support this thing, what's the probability that you could take a random sample of 50 subjects and get a p-hat of 54%? Or even smaller. 65% is what the null hypothesis was. What's the probability you could take a sample of 50 subjects and get only 54%, or even a number less than that? What's that probability? Compute that probability for me. Emily gave me this. Come on, compute the probability. What's the probability that if the null is true, I could get sample data like we got, or even further from the null? What did I just spout off? Definition of p-value. You've already computed that probability. So on the test, if I say, what would the chance be of this? That's the p-value. That's what a p-value is. There's a 5.1% chance that you could get data like this if the null were true. So the fact that we failed to reject, we barely failed to reject. Right? We say, if you get less than a 5% chance, less than or equal to a 5% chance, then you're going to reject the null. And we got a 5.1% chance. So, and unfortunately, scientific journals hold that as a cutoff. They would say, sorry, you didn't show anything. We're not going to publish that paper. But if we had got 0.0499, they'd be all, ooh, boy, you really got something here. Right? But it's not like that. It's a probability. So this probability is essentially the same as this probability. So that's why I like to quote the p-value. I don't like to just quote reject, fail to reject. Because the reader needs to know, well, you might have failed to reject, but you barely did. So yeah, I think something's going on. I think the politician has a point. Right? So I maybe need a little bigger sample to prove it, but he's got a point. All right, so that's enough of that soapbox. Right? Here's their calculation of the test statistic by hand, getting negative 1.63, which is what we got here. Right? Question?
Yes. So what did you say was the p-value? Like, what were you exactly going to say?
What's the definition of p-value? It's the probability that you could get sample data like this and like this, right? It's the probability you could get sample data with a sample proportion of 0.54 or a number even further from 0.65 if the null is true. If it's really 65% in the population, getting 54% in a sample is possible, but not very likely. But it's a little too likely compared to the significance level. A little more likely than the significance level, so we still fail to reject. Got it? I'm going to do my best to beat that into your heads of what exactly is a p-value. But don't feel bad. Like I said, I work with MDs, I work with PhDs in all kinds of sciences and really, really smart people, and nobody can understand what a p-value is. They're all like, all I know is if it's less than 0.05, that's a good thing, right? They don't know what it is. They can't tell you, and I like to tease them, what's the P and p-value stand for? And they look at me like, it stands for something? What does it stand for? Probability. See, you're smarter than them. It stands for probability. Well, probability of what? Probability you could get sample data like you got if the null's true. That's a p-value. As a picture, p-value is a probability. It's the probability of being where you were. We had a test statistic of negative 1.63 or further away from the null. And it's just computed from the standard normal distribution. But it's built into your calculator, so you don't have to do that calculation. But okay, let's jump down and do this one from our class data. I went out this morning and looked on the CDC website to see if they had any national statistics on smoking rates. And boom, it was easy to get. Here's what they said. Nearly 19 out of every 100 adults aged 18 to 24 years, which is 18.7%, right? This is nearly 19 out of 100, said they were smokers. And then 25 to 44 was 20.1, and so on. Since most of our sample falls in this age range, I thought, well, how does that compare to what we thought? So, according to the students in MA140 in fall of 2015, there were 260 people who were in that age group out of 365, right? So these, I just said greater than 24. I didn't break it into their other age groups because I'm interested in this one age group. Right? Now, what percent of them said, yes, I'm a smoker? Well, only 6.15% said they were a smoker. Right? So, test the claim. Test the claim that the rate at Washburn in that age group is less than the national average. You do it yourself. Conduct that hypothesis test. Go through all 4 steps. And don't say, what, there's steps?
You said 6.8% is what we found?
6.15 of 260. I'll flip back to that in a minute, make sure everybody's got what they need off of this slide. I forgot to put on this slide, use alpha equal 0.01. So I'll put this up and write it here. Alpha equal 0.01, which means we'll be 99% confident of our result, of our conclusion. I see people working on their calculator already. What's the first step? Write the hypotheses out. So Emily, you better have some there, she's writing them down. Now, I don't mind if you go to the calculator first, but it helps if you'll write down the hypotheses first, because in your calculator you have to choose the correct alternative, and if you've got them written down, that makes that easy. If not, you're kind of guessing, and then it may not actually fit the true scenario. You guys got hypotheses? Okay, perfect. That's right. You got the same thing?
I'm working on it.
You've already worked it all the way out?
No.
Oh, I see. Okay. What you got? Okay, good. And then you're supposed to check assumptions. Can we use one prop Z test? What do you think? Can we use... Yep, that's right. Yeah, you wrote it. Good.
Yeah, I was like, what?
Just know that your calculator has to have it that way. So, okay. So what do you think? Can we use one prop Z test? You got answers?
Is that right?
That is right.
Okay.
Yep. Now go to your calculator and work this thing. You didn't bring... Well, here, you can have Thomas's. No. I'll give you mine. Somebody's borrowing yours? So what you're saying is you're too nice.
I guess so. Thank you.
And I confused the... You got an answer?
No. So that's the...
Look what you did.
That one.
That one. Yep.
Is it one sample or two samples?
This is one sample.
But I thought like one of the samples was those people and the other...
Thank you. I thought you just accidentally hit it, but what she just did is a very common mistake. So I want to mention it. I wouldn't have thought of it. But she said she grabbed two prop Z tests because, well, you got a sample from the national, and then you got, and that's true. Those numbers that they quoted, that's not a population parameter. It came from a sample. But we're going to treat it as if it's a population parameter. They don't give us any information about that other sample. We don't know sample size. We don't know anything. So we're just going to accept it as this is the national average. So it's one prop. Yeah. So you're actually thinking it through better than most of us. You got an answer?
I think so.
Yep, that's what I got. Good. And what did you write as a conclusion? Wrong conclusion. Look at that. P-value. What does the P and P-value stand for?
I wrote that down wrong. The probability.
Yeah, so what is the probability? It has to be less than...
1.
Look out here.
So, okay.
Another common mistake. This turned out to be a good one. Just a minute. They had their hand up first. Question?
Yeah.
Go ahead.
You round up or down?
You round to the nearest whole.
Okay.
Yeah.
So nearest whole.
Nearest whole. So most of you have gotten through that step already without me warning you that it was coming up. But when you go to your calculator, they didn't give us X, but your calculator wants X. So how do you get X? Right, so X is N times P hat. They told us that P hat, well, they told us N was 260 and that P hat was 0.0615. And that gives you what? It gives you 15.99, which then the nearest whole is 16. Did anybody get a domain error by entering 15.99? Yeah, if you don't enter a whole number, you'll get a domain error, which should trigger your memory.
I put 1.6. Yeah, I was like, that's not really
Oh, okay. Now I lost the thought I was going to have on... it'll come back. Somebody else was doing something I wanted to see, but...
Okay.
Glad I wasn't under that.
This isn't my calculator looks like for that. So if it is like the P's, the arrow's pointing
Yeah.
towards the P, so it
No,
would be that one.
pick that.
So-
P0 is your number, 18.7.
Okay.
So
it's
this-
just, it's pointing to the left. You use the arrow that's pointing to the left.
Right. So this prop is P less than P0, and this is P0.
Oh, okay.
Okay? Okay, so let's bring it back together here, and null and alternative hypotheses look like they were on the last one we did, but it's 0.187. Right? Because that was the national average. And then X, we just did X. On your calculator, X is 16. And I jumped over P0. What is P0? 0.187. If you did this, you don't have to raise your hand or anything, but a common mistake is to put this number, 0.0615, which is P hat, put it in right there. Did anybody do that? If you do, what do you get for a p-value?
I don't know, I didn't enter it because I felt like it was wrong.
Well, good, you caught yourself. If you did that, you would get a p-value of 0.5 for a one-tailed test and 1 for a two-tailed test. Because now what you've done is you said, my sample data is exactly the null hypothesis. So that's a probability of 1 you could get data like this if the null is true. Right? So if you ever get a p-value of 1, you look and see if you made that mistake.
So why are you using 0.187?
That's the hypothesized value. Right? The sample data is X and N. Right? So N is 260. And then we want, I wrote it wrong over there, I didn't realize it, but it doesn't say P colon, it says prop colon on your calculator, right? But prop means the proportion in the population. So prop is P, and then you want to use less than P0. Okay, so now when you run it, you get a p-value of what?
0.063 times 10 to the negative.
Yeah, oh yeah.
I got, oh yeah, that's what I thought. So
Right? Now, I saw more than one person write this down as their p-value, go to make the conclusion, say, oh, well, that's bigger than alpha. So I'm going to fail to reject. I don't have sufficient evidence to support the claim. But remember, what is a p-value? What does the p and p-value stand for? Probability. Can a probability be bigger than 1? No. So, oh, I did something wrong. You go back and look at your calculator and you see out here, E negative 7. Is that what you were going to say? So what is that as a decimal? You don't have to write it out. This is fine. But 0.000001063. Now, what is the p-value again? I keep forgetting that. The probability that you could get sample data like we got, or even further from the null, if the null is true. So if the rate at Washburn is the same as it is nationally, there is a 1 in a 10 million chance that you could get data like you just got. So therefore you what? You reject the null hypothesis. Say, well, it is not 0.187 at Washburn. It's less than that. So we have sufficient evidence. There is sufficient evidence to support the claim that the smoking rate at Washburn is less than it is nationally. Boom is right. Glad of that. Okay. Sufficient evidence to support the claim that the smoking rate at Washburn is less than the national average. Whenever you write that sentence, support the claim is always whatever the alternative hypothesis is, in words. Right? So don't make the mistake of saying, there is or there is not sufficient evidence, and then write out the null. Always write out the alternative. Right? Okay? Man, this stuff's easy. Any questions? I still see some of you trying to get numbers in and all that. Okay, then you got a question?
No, I'm
You're answering her question. Okay, good. Anything else? Yes?
What did you say the claim was?
What?
What did you say the claim?
The claim is always the alternative. But you don't write it like that. You write it in words. So the claim is still up here on the screen. Conduct a hypothesis test of this claim. The claim is at Washburn, the rate is less than the national rate. Right? So we have sufficient evidence to say that the rate at Washburn is less than 18.7%. Okay? Everybody happy? All right. Have a great weekend. We will see you on Monday.